Assalamu alaikum everybody. This is the concluding part of our greedy algorithms lecture. So greedy algorithms 2. The objective or the objectives of this lecture are only three this time, so it's going to be very short hopefully. First, we will briefly discuss about codes and data compression. Both of them meaning the same thing actually, because that's actually the objective of our algorithm that we shall study in this lecture, which is called Huffian coding algorithm. So after we briefly talk about data compression, we will then discuss about Huffian coding algorithm. Okay, and finally, after discussing the algorithm and how it works, we will prove its correctness. So correctness of Huffian coding algorithm. Obviously, we are discussing Huffian coding algorithm because it is a greedy algorithm. Okay, so that's our objectives, or those are our objectives for this short lecture, inshallah. Okay. So codes and compressions or compression. Suppose we have 100,000 characters data file. So a data file consisting of 100,000 characters. And we wish to either store this file, save it on a disk, or transmit it over the network. Okay. Suppose further that the file contains only 6 different characters as listed here, A, B, C, D, E, and F. And the characters appear in the file according to these frequencies. These frequencies are in thousands. So A, for example, occurs 45,000 times in our file. B occurs 13,000 times, and so on. Now, of course, we all know that characters are not saved as we see them display on the screen. They are not saved as in symbols like that. Rather, they are saved as binary data. So they have to be encoded into binary form, consisting of only zeros and ones. Okay, so this is normally done using what is called binary encoding or binary code. So binary code encodes each character into a binary string consisting of zeros and ones, and the code for each character is called the code word for that character. So the string of bits that will represent character A is called the code word for character A. All right. Now our objective in this Huffian coding algorithm that we're going to see is to find a binary code that will encode the characters in our file with the fewest possible bits, or with the fewest bits possible. And that's basically what data compression does. It reduces the size of a file to the minimum possible. So we have a file of 100,000 characters, and we want to reduce it to the minimum possible bits. Okay, in other words, we want to compress the file as much as possible. Now here are some of the schemes that are possible. Some of them we already know because they are standard. Okay, so these are our characters, 6 of them, and these are their frequencies, as we said. Now we all know the ASCII encoding scheme. In ASCII encoding scheme, each character is allocated 8 bits. Okay, so this is the encoding for character A in ASCII scheme. Similarly for B and so on. So if you apply ASCII encoding scheme to represent our file, it will consist of 8 times 100,000, and therefore we will have a total of 800,000 bits. Obviously, this is without compression. Okay, now suppose you want to be more general and use Unicode instead. Then we know that in Unicode each character is represented using 16 bits, and therefore our file will be represented into 1,600,000 bits. Okay, so 1.5 megabyte, if you like, 1.6 megabyte. Okay, so again, this is obviously without any compression. Now, in trying to compress the file, there are two main approaches. We could use what is called fixed length scheme. So here we just look at the possible values that we have. There are 6 of them, and with 6 different symbols, we don't need more than 3 bits to represent each one. Even if there are 8, we can still do that with 3 bits. Okay, so with that approach, we could have just allocated this scheme. So A will be 000, B will be 001, and so on. Basically, just choose 6 of the 8 possible combinations that you can have with 3 bits. Now, if you do this, definitely there is a compression this time, because instead of using the standard 8 bits, we are using only 3 bits, and our file will be represented using 300,000 bits. But there is an even better approach, and that is called variable length encoding. So in variable length encoding, we don't give a fixed length, a fixed code word for each character. Rather, we allocate the bits according to the frequency of the character, where the words that have more or that occur the most, so that has the highest frequencies, they will be allocated fewer number of bits. So since A is the one that has the highest frequency, we're going to allocate it only 1 bit, which is 0. Okay, B will be allocated 3 bits, and so on. Okay, so the least frequent characters like E and F here, they are being allocated 4 bits. Okay, but of course this has to be done systematically, and this is the whole idea of Huffian coding that we're going to see. Okay, so as I said, in a fixed length code word, in a fixed length encoding, each code word will have the same length as we saw there. But in a variable length code encoding scheme, the code words may differ in length. Okay, as we just saw, if we follow this allocation, the variable length encoding that we have here, we will allocate a total of 224,000 bits. Obviously, this is much better than the previous encoding scheme. This is the percentage in terms of saving. Okay, by using this variable length, comparing with ASCII, we will have saved 72%. Okay, because instead of 800, we will have only 224. Okay, so we achieve 72% advantage, if you like, or compression. Whereas with Unicode is even better. We will have achieved 86% in terms of compression, comparing our variable length encoding here against the Unicode. Okay, it is also still better than the fixed length with a lower percentage, of course, because we're not using many bits in the fixed length, only 3 bits. So the percentage gain will be 25%. Okay, so this is the idea of this encoding scheme. However, like I said, it is important to encode the characters using the variable length such that they can be decoded easily. You shouldn't just assign the variable code words randomly. As we're going to see in these 2 examples, how do we decode after we assign variable length code words to our characters. Suppose, for example, or in this example 1, we assign 0 to A, 0, 1 to B, and 1, 0 to C. And now suppose we want to decode this sequence, 0, 0, 1, 0. Okay, you will see here that there is some ambiguity. Okay, because for 0 there is no issue, it's going to be A. But here, the next 0, is it for A, or is it supposed to be considered together with this 0, 1 to be B? This is the issue. Okay, so are we going to get AAC or ABA? So obviously there is an issue here. When assigning the code words using the variable length, we must make sure the resulting string can be decoded back to characters. Okay, so look at our second example. Suppose instead we assign A is still 0, but B as 101 and C as 100. Now with this sequence, we can easily decode. There is no ambiguity at all. If we see 0, definitely is A. 0 definitely is A. Okay, now if we see 1, 0, 0, then we conclude that it is C. The question is, what is the difference between these 2 codes? Okay, the difference is what we call prefix code. The second one is called prefix code, whereas this first one is not. So what do we mean by prefix code? In prefix code, no code word will appear as a prefix to another code word. Okay, so if you have 0, then no other character should start with 0. Okay, so clearly this is not prefix code because we have 0 and here we have another character starting with 0. Okay, so that is very important. In prefix code, no character appear before another code word. No, let's see it here. So in prefix codes, no code is a prefix to another code. Okay, if you assign a particular code, then no other code should begin with that. If you have that, then you have what is called prefix code, and in that case you can easily decode any string that you are given without any ambiguity. Okay, so that's what we are asking here. Why should we want this? Because it simplifies decoding. It removes ambiguity. Once a string of bits matches a character code, just output that character with no ambiguity. Okay, again, also no need to look ahead and see. Just work on the current one. Okay, now we can use binary trees for decoding codes that are in this format. Simply you will be going left, for example, if you encounter a 0, and you will be going right if you encounter a 1 in the character that you are trying to decode, or in the string that you are trying to decode. So you keep going left or right until you reach a leaf node. The leaf node will contain the actual characters. Okay, so the leaves are the actual characters. We're going to see example in the next slide. Okay, suppose we have these codes, or these characters A, B, C, D, E, F. Okay, so now if you can see that A is 0, so if from the root you just go to the left, first time you have a leaf, and that will be represented, that will be representing the character A. Okay, now 1 0 0 is going to be represented as you see here. So you go to the right, you go to the left, and you go to the left. Okay, C is being represented as that. And similarly for B and F and E and D. Okay, you can see that this is a full binary tree. I hope you recall the definition of full binary tree. Full binary tree is one in which each node is either a leaf or it has exactly 2 children. One child is not allowed. Okay, so you can use full binary tree to represent the variable code words. So this is an example. Of course, these are the code words based on what we have just seen. A will now be 0, C is 1 0 0, and so on. Now suppose we have a sequence of zeros and ones. So we have a string like this of zeros and ones. How can we decode it to know exactly the characters represented by that sequence? All right, so what we do is we keep starting traversal from the root and follow the direction. If we see 0 0, go to the left. If we see 1, we go to the right until we reach a leaf node. Okay, once we reach a leaf node, that leaf node will tell us what character we have so far. Then with the rest of the code, you will start another traversal again from the root. Again, keep going left or right until you reach a leaf node. Okay, so let's do it with this example. Obviously, 0 here tell us to go to the left, and we're going to find A immediately. So this first 0 means A. All right, start another traversal. We have another 0, so that 0 obviously means another A. Okay, start another traversal. This time we see 1, so 1 takes us here, which is not a leaf. So what is the next character? 0. 0 tells us to go to the left, and again this is not a leaf, so we should not stop. Now another 1 asks us to go to the right. This time we reach a leaf. Therefore, what we have traversed so far represent a B. 1 0 1 is a B. As you can see here, this is a code word for B. Okay, so we're going to replace those with B and start another traversal again with the rest of the sequence. So 1 will take us to the right, 1 again will take us to the right, this time 0 will take us to the left, and finally 1 will take us to the right, and we're going to encounter E. So it means our string actually is AABE. So this is basically how you decode a string of bits if you are given. Just traverse the tree repeatedly. Each time you reach a leaf node, you have found one character, and then restart the traversal from the top. All right, so if you have a variable length encoding, you can always represent it as a full binary tree, and it will allow you to easily decode any string just by traversing the tree. Okay, let's take some properties of prefix codes before we proceed. The first one says an optimal code must be a full binary tree. A tree where every internal node has 2 children. So as I said at the beginning, you don't just encode the characters randomly. You have to do it to have the prefix property. And here we are told actually the prefix property is going to be a full binary tree. Okay, that an optimal encoding scheme must be a full binary tree. A tree where every internal node has 2 children. Okay, for n leaves, this is again from our knowledge of data structure. We know that for a full tree, the number of leaves is going to be 1 more than the number of non-leaves. So for n leaves, there are going to be n minus 1 internal nodes or non-leaves. Now, the number of bits to encode a file, the total number, which is considered to be the cost of the tree T, represented by that encoding, is denoted as BT and is given by the following equation. Okay, so the B there is coming from the bits, the number of bits needed to encode the characters in the tree is given by this summation. Okay, summation for over all characters in your characters in your alphabet. This C is called the alphabet. Okay, that is the characters that you are trying to encode, the set of characters. Okay, so the cost of the tree T, representing your full binary tree, will be represented as summation of the frequency of each character times its depths in the tree. This DTC means the depth of character C in the tree T. So if you add these products for all characters in the tree, you will have what is called the cost of your tree. Okay, so where, as I said, C.freq is the frequency of character C, and dt of C is the depth of the character C in the tree T. How deep is it? Okay, you will see that this depth actually corresponds to the code length of the character C. Just to show you more clearly, if you are trying to find the cost of this tree, then it's going to be, you can see, for example, the depth of A is 1. Just one link will take you to 1. And you can see clearly this is 1 bit. What about the depth of C in our tree? It's going to be 1, 2, 3, which correspond to the number of bits for that character. What about F? Is 1, 2, 3, 4. So the depth is 4, and it's equivalent to the number of bits representing F. So if you want to know therefore the total cost of your tree, it will be how many A's that we have. These numbers here are representing the frequencies, remember? So there are 45 times 1, 1 being the depth of the character A in our tree, plus 12 times 3, 3 being the depth of C in our tree. Okay, and so on and so forth. 13 times 3 plus 5 times 4 plus 9 times 4 plus 16 times 3. This is the total cost of this tree. In other words, our file, if you recall, we are trying to compress a file. If we want to know how many bits we're going to have, this is how we're going to compute it. Okay. So 45,000 in this case, because we told the frequencies are in thousands, so it's going to be 45,000 times 1, 12,000 times 3, and so on. This is actually how we got the 220, what did we say? 224,000 bits. This is actually how they were computed. Okay, so this equation is very important. We're going to use it a lot later. It tells us the total cost of our tree is simply the sum of the products of the frequency of each character times its depths in the binary tree that is used to find the encoding scheme for our variable length encoding. Okay, so let us state our problem formally, and then we will see how Huffian helps solve this problem. Okay, optimal prefix encoding problem. This is exactly what the Huffian algorithm tries to solve. So input. Suppose we are given an alphabet C corresponding to n letters. So alphabet is simply a set of characters. So we are given an alphabet C consisting of n letters, C1 to Cn, each with its corresponding frequency, ci.freq. So each character has an attribute .freq, which will give us the frequency of that character. The question is, construct a full binary tree T to define a prefix code that minimizes the total cost of your alphabets. Okay. So we want to find the full binary tree T that will minimize this total cost, BT. Okay, so this is our target, to find a full binary tree T that define a prefix code that minimizes the total cost. Total cost BT, as we defined before, is simply the summation of the frequencies times the depth of each character in our tree. All right. Huffian code algorithm. Now, Huffian developed a greedy algorithm that solved the optimal prefix encoding problem. Like all greedy solutions, the proof of correctness of Huffian code algorithm relies on two things. One, greedy choice property. Does the Huffian code algorithm has greedy choice property? And is that greedy choice property safe? This is one aspect. The second part is, does it have optimal substructure? Remember, optimal substructure, the solution to a problem, the optimal solution to a problem contains within it optimal solution to subproblems. So this is what we're going to prove later. Okay, we shall first discuss the algorithm before proving its correctness. The algorithm uses a minimum priority queue, a mini heap if you like, queue, to store the characters in the alphabet C as 3 nodes according to their frequency, as we shall see in the next slide. It then builds the tree bottom up by dequeuing the front 2 trees, merging them, and enqueuing the resulting tree back into the queue. The process is repeated until there is only one tree in the queue, which is the Huffian code tree. Let us see the algorithm in detail. So the algorithm receives the alphabet C along with its frequency. So each character comes along with its frequency in the alphabet. Okay, it first computes how many characters are there, save it as n. Then it creates a queue using min heap, using all the characters in C. So it creates a queue, it uses the characters to build a heap. Okay. Now it repeats from 1 to n minus 1. So if there are 10 characters, the loop only need to repeat 9 times, n minus 1. So what does it do? Each iteration will first create an empty node called Z. Okay. Then it will allocate the queue from the queue. Remember, we initialize the queue with all characters. So it will dequeue the minimum one, save it X, and assign it to the left subtree of Z. Remember, we created a node Z. Each node will have a left and right subtree. So the left subtree of Z will be allocated the first element that we dequeue. Dequeue another element, the next minimum, call it Y, and assign it to the right of Z. Okay. Now, compute the frequency of add the frequencies of both X and Y. So X.freq plus Y.freq, add them up and assign the result as the frequency of your Z. So our node Z is complete now. It has a node whose content is the frequency of the sum of the two frequencies of the left node and the right node. Now enqueue this node Z back into the queue. So insert Z into the queue. Obviously, since we are using min heap, it's going to be positioned in the correct place. So repeat this process until n minus 1. So meaning actually there will be one node left in the tree after this loop. Return that one node. So extract it and return it. This is basically the idea of Huffian code algorithm. The algorithm is better explained with an example. So we're going to take an example. The same example that we started with. Suppose you have this sequence of characters. Of course, we remove the thousands. So although this is 45,000, we just use 45. So the algorithm says first create a queue based on the frequencies of each character. Okay, so obviously F has the least frequency with 5, so it's going to be at the front of our queue, followed by E, followed by C with 12, B with 13, D with 16, and so on. Now start the loop. The loop says dequeue the first two. Okay, create a new node Z. The value inside the node itself will just be the sum of the two frequencies, so 5 plus 9, which is 14. And the left of that node will be the first one you dequeue here, so it's going to be F. And the right subtree of that node will be E, with a frequency of 9. Enqueue the node that you just constructed back into the queue. So if you do this, this is what you have. Okay, this is the tree we just created with the content of its node being the frequency of 5 plus 9. Okay, 5 plus 9 is 14. Okay, the two elements that you just decode. Now the F will be to the left, the right will be the E. Now if you encode this back, of course it's going to be placed according to its priority. The priority is the frequency. So obviously it's going to be bigger than 12, bigger than 13, but less than 16. So it's going to be placed right here. That's why you see here we see C and B, and then the new element, and then the rest of the elements. So this is iteration number 1. Remember we said for n elements, in this case we have 6 elements, 1, 2, 3, 4, 5, 6. We only need to do n minus 1 iteration. So we're going to do this 5 times. So next you're going to decode the two front elements, which are C and B. Their total frequency will be 13 plus 15, which is 25. To the left we're going to have C, to the right we're going to have B. Now encode it back into the queue. Obviously 25 is bigger than 14, bigger than 16, but less than 45. So this is what you're going to have. Okay, the new node is placed here. Repeat the process. Decode the next two. If you add them up, you're going to have 30. 14 plus 16 is 30. So 30 is still less than 45. So it's going to appear between 25 and 45. That's what you are seeing here. Notice that the left is the 14. So this node, this is the left of our new node, and the right is 16. Okay, the total is 30. So this is the tree you're gonna get, and that's what you're gonna put back into the tree between 25 and 45. So it's gonna be here, as you can see here. Okay, next we decode these two. Okay, if you add them up, you're gonna get 55. Now for the first time we have a value bigger than 45. So it's gonna be placed after the 45. To the left we will have this, to the right we will have this, and the node itself, the root of that subtree, will have 55. Okay, so this is what you're gonna have after doing that, after merging these two and encoding back into the tree. Okay, so one more iteration to go. You're gonna decode this and this, add them up, and put back into the tree. If you add them up, you're gonna have 100. 45 plus 55. Remember, we have 100,000 characters in our file. So this is what you have. Okay. So now that we have only one node in the tree, return it as your Huffian code tree. This is basically what Huffian code will do. Obviously, once you have this tree, now allocating the code word is straightforward, as we discussed before. Just keep going to the left or right until you reach a leaf node. In this case, once we go left, we will find A. So the code word for A is going to be 0. The code word for B is going to be 100. This is 101, and so on, as we saw before. So this is basically what Huffian code algorithm is. There are two important points to note at this point. One is here when you decode two elements, actually it doesn't matter whether you make the first one to go to the left or to the right, but you have to be consistent throughout. Okay. However, to make sure we always get the same tree, we're going to require that you must put the first one on the left. Okay. So for consistency, the first element, decode, should always be put on the left side. Okay. Even if you put it on the right, you will still end up with an optimal tree. But this is just for consistency. For consistency, the first one you decode, put it to the left. and the second one you dequeue, put it to the right. Now, the second, probably most important point is to note that the algorithm actually has a greedy property. The greedy algorithm places the characters with the least frequencies at the deepest level. This is basically the greedy property of the Huffman code algorithm. As you can see here, the least frequent elements, 5, F with 5, and E as 9, are being placed at the deepest level. This is the greedy property of the algorithm, and it is natural, it is very intuitive. We are trying to economize and allocate small number of characters for those that occur the most, and allocate the bigger code length to those that occur only very few. So of course, as you go deep in the tree, you will be allocating more bits. Therefore, those that you put in the deepest part should be those with the least frequent occurrence. Okay, that has the lowest frequency basically. This is the greedy choice that the algorithm is doing or is using. And we're gonna prove this in the rest of the lecture. We will also prove that the algorithm satisfies the optimal substructure property. Before we attempt to prove the correctness of Huffman code algorithm, let us compute its running time. This is the algorithm once again in full. Now we notice that the first thing we do is, after the computing n, is we create a queue with the characters as they are. So this will obviously cost big O of n because they are n characters. Just putting them to construct an initial queue, just put them in the array, breadth first order, based on the frequency, will cost big O of n. Okay, now the loop. Each time we are extracting 2 elements, well, each extraction, because we are dealing with min heap, will cost log n. Okay. Also, inserting the new node after it is computed will cost log n. But we are doing this about n times, from 1 to n minus 1. Therefore, the overall running time actually is n log n. Okay, this loop will cost n log n. The computation here will cost log n, but we are doing it n times, so n log n. N log n plus the initial construction of the queue, which is big O of n. Overall, you have n log n. Therefore, the running time of the Huffman code is n log n. Okay, Huffman code algorithm, that is.